every week, the average for every week for that 3 years. And that's how you got the straight line. Now, what this is showing is that this is what the power factor of this area. The top line is power factor. And this is what the power factor usually is. This is the axis for the power factor. And so the power factor is usually in the region of 0.8, 0.88 or 0.86. And what this is showing is that when we implemented the power factor correction project, it immediately moved up to 0.96. 0.96 or 0.88 can be looked at 96% or 88% respectively. Now, this graph is actually for a pilot project at the physics department, because as I mentioned before, we test everything before we decide to go large scale. Now, this was very encouraging, because what it showed us is that as soon as the power factor went up, the bottom graph shows the KVA, and KVA went down. Now, JPSCO has several different types of billing regimes. Let's call them that. You have your rate 10 customer, your rate 20, your rate 40, and your rate 50. Now, UE is a very large customer, so we're rate 50. Now, as a result of that, we're billed for about kilowatt hour and also KVA. Many other businesses may also be billed in that way. And so KVA is a very important parameter for us. Currently, for every 1 KVA, you pay $1,165. So we're talking about money here. So if we are able to improve our power factor, we saw that our KVA went down, then this is a marvelous project. And so based on this data and this analysis, we were able to prove to campus administration that this thing worked. In fact, when we ran the numbers, we were able to show, using $2,008, that this project paid back for itself in 9 months. Now, we don't have a lot of money, but if somebody comes to you and tell you that you can spend some money to save some money, in 9 months' time, pay back for itself, and it would last for 20 years. I mean, I did not say anymore. That is definitely something you want to do. So what we decided to do was to go wide scale. Now, we're facing another challenge. When persons think about power factor correction, they think about, for example, UE has one main electricity feed entering the campus, 1 metering point. As large as the campus is, 1 metering point. So even businesses that exist on campus, they're not billed by JPS, they're actually billed by UE after being billed by JPS. So anything that we do on campus is strictly JPS we deal with. So we have a 24,000 volts line coming in. And from there, it is distributed campus-wide. Persons say, hey, you're doing power factor correction, correct from the point. I mean, it sounds logical, because at the end of the day, JPSCO will see that correction. But again, we do our own research. And in addition to what Mr. Horton, as in terms of consultancy we got from him, very solid consultancy, we're able to devise a plan where instead of doing a single point, which was the conventional and traditional way to do it, we went ahead and installed variable capacitor banks at the several locations campus-wide. In all, we did 19. Now, there are other professors from Trinidad, for example. They are professors in engineering, you know. We do the engineering, so we don't know what we're doing. You know, this was a pedestrian assessment, foolishness. But while we were able to get support, we had the data. And because we're able to measure it and show that it works, we're able to get some amount of support. And from that, we're able to get support to install some 19 of these banks campus-wide. It ranged from size of 25, they're rated in kVARs, from 25 kVAR to as large as 150 kVAR. Now, what that allowed us to do was that we could use our own skills, our own talents, because we're not dealing with 24,000 volts. We're now dealing with a pad mounted transformer on the secondary side, 480 volts. You have some large current, like 100 amps or 800 amps, but we're still dealing with manageable values that we, within our capacity and Caribbean ESCO, their engineers, could do. We didn't have to get some top person, so that significantly reduced the cost. The end result is that by distributing the power factor campus-wide, JPSCO still saw our power factor increase on their side, and it makes perfect sense. But there's one other benefit we got that people don't really know about, and that is, even though power factor is really about KVA, we were able to show that power factor, that graph is a little further down. We were able to show that power factor impacted kilowatt as well. Now, Yes, we're able to show that power factor impacted kilowatt, which is very important. This is about 5% reduction in kilowatt. Now, the unit cost per kilowatt for a 850 customer is $3.30 something. But that value is also impacted by the cost of oil. So for every kilowatt you use, you pay the same thing for fuel and IPP. And fuel and IPP ranges from what? Sometimes even $19 for every kilowatt, sometimes $14, and it's very vulnerable to what happens on the world market. So you see one measure, by being able to measure it, we are able to show that it impacts kVA and kilowatt, and we're able to calculate the savings. Now let's speed up a bit. We also had another project called electronic ballast, where the magnetic ballast, those had poor power factor, and electronic ballast had better power factor. So we're able to show that it also impacted the usage. Now there's one point I must bring out on this graph, and that is the physics department, like the University of the West Indies, has a seasonal load. Jamaica don't necessarily have a season like winter, autumn, etc. But there are times when it rains and there are times when it's dry. So we can say we have a wet and dry season. But in the case of UWI, we have season where students are on campus and when students are not there. And so you actually see a big difference in terms of how energy is being utilized. In addition to that, departments with the autonomy that they have decide that they want 2 more AC units, they want to expand their lab, they want to have special programs that run additional hours into the night. So they tend to change their pattern of energy use significantly. And so this graph actually reflects that. So there are times when it's up and times when it's down. In fact, right after we corrected the power factor and the kVA went right down, you see it start to go up again. You ask what happened there. Right after we finished this project, they opened a new virtual lab at physics that had some 50-odd computers in there, put in about 4 mini-split AC units, and say we're offering a higher quality product now to students that they can come and use a virtual lab. Now that's positive, because we're offering an educational product. But guess what? That erases the savings that we just gained. But that is still positive because they're back at the levels they were before we did the measure. Imagine if we didn't do the measure. Now, just make a note of that point. That actually presents a problem in the long run, because there are persons on campus who, if they don't see $1 savings reduction in the JPS bill, then they say we're not doing anything. But you could say that we did something. It actually went down, but because they changed their pattern of usage, it went up. So I just wanted to sum up what I just said into one point. Part of the whole energy conservation and efficiency is that you have to continue to monitor what you're doing, and you have to be able to substantiate what you're doing, because not all the time you'll actually see your savings in terms of dollars and cents because of many variables, changes in patterns of usage, as well as how JPSCO changed their rates. Now, there are many benefits from power factor correction. I'll just highlight the one at the bottom, where we have several pad-mounted transformers, and they all have various ratings. Some of them are 300 kVA, some are 500 kVA. Whenever you're adding additional load to a transformer, if you load that transformer to greater than maybe 85 to even 95%, then you can have many problems. So when you do a power factor correction project and you can reduce that load, it prevents you from buying a new transformer. Now, these transformers are not cheap, very expensive. And so just by doing this project, it also saved us money in that regard as well. Now, very quickly, in terms of lighting retrofits, we went from T12s to T8s, and we also did a LED pilot project. Our results from that, I was hoping to write here, but if I write, I can't talk. So probably you can make some notes of this. We did some very simple tests. For example, we had 3 mock things set up. One was 2 T12 lamps in parallel. Another, and those 2 T12 lamps, in the case of T12s, for every lamp you have, that is the tube, it requires a ballast. So 2 lamps, 2 ballasts. In the case of the T8s, however, using electronic ballast, 1 ballast, some of those that we got through Carbonesco, can serve up to 4 tubes. So it's no longer a 1-to-1 relationship. So back to the example, 2 T12s at 40 watts use 2 magnetic ballasts. And when we measured the kilowatt from that, or the watts in this case, we got in the region of 87, 88 watts. Those 2 lamps were drawn.